Hadoop 2.2 brought about architectural changes to MapReduce. As MapReduce has matured, people have found that it can be used for more than just running MapReduce jobs. But to keep each new framework from having its own resource manager and scheduler that would compete with the other framework resource managers and schedulers, it was decided to have the resource manager and scheduler to be external to any framework. This new architecture is called Yarn, yet another resource negotiator. You still have data nodes, but there are no longer task trackers and the job tracker. You are not required to run Yarn with Hadoop 2.2. MapReduce version 1 is still supported. There are two main ideas with Yarn. Provide generic scheduling and resource management. This way, Hadoop can support more than just MapReduce. And the other is to try to provide a more efficient scheduling and workload management. With MapReduce version 1, the administrator had to define how many map slots and how many reduce slots there were on each node. Since the hardware capabilities for each node in a Hadoop cluster can vary for performance reasons, you might want to limit the number of tasks on certain nodes. With Yarn, this is no longer required. With Yarn, the resource manager is aware of the capabilities of each node via communication with the node manager running on each node. When an application gets invoked, an application master gets started. The application master is then responsible for negotiating resources from the resource manager. These resources are assigned to containers on each slave node, and you can think that each task then runs in a container. With this architecture, you are no longer forced into a one-size-fits-all. The name node is a single point of failure. Is there anything that can be done about that? Hadoop now supports high availability. In this setup, there are now two name nodes, one active, one standby. Also, now there are journal nodes. There must be at least 3, and there must be an odd number. Only one of the name nodes can be active at a time. It is the journal nodes, working together, that decide which of the name nodes is to be the active one. And if the active name node has been lost, whether the backup name node should take over. The name node loads metadata for the file system into memory. This is the reason that we said that the name node needs large amounts of RAM. But you're going to be limited at some point when you use this vertical growth model. Hadoop Federation allows you to grow your system horizontally. This setup also utilizes multiple name nodes, but they act independently. However, they do all share the same data nodes. Each name node has its own namespace, and therefore has control over its own sets of files. For example, one file that has blocks on data node 1 and data node 2 might be owned by name node 1. Name node 2 might own a file that has blocks on data node 2 and data node 3, and name node 3 might have a file with blocks on all 3 data nodes. Hadoop has awareness of the topology of the network. This allows it to optimize where it sends the computations to be applied to the data, placing the work as close as possible to the data. It operates on maximum bandwidth availability for reading the data. In the diagram, the data we wish to apply processing to is block B1, the dark blue rectangle on node N1 on rack 1. When deciding which task tracker should receive a map task that reads data from B1, the best option is to choose the task tracker that runs on the same node as the data. If we can't place the computation on the same node, our next best option is to place it on a node in the same rack as the data. The worst case that Hadoop currently supports is when the computation must be processed from a node in a different rack than that of the data. When rack awareness is configured for your cluster, Hadoop will always try to run the task on the task tracker node with the highest bandwidth access to the data. Let's walk through an example of how a file gets written to HDFS. First, the client submits a create request to the name node. The name node checks that the file does not already exist and that the client has permission to write the file. If that succeeds, the name node determines the data node to where the first block is to be written. If the client is running on a data node, it will try to place it there. Otherwise, it chooses a data node at random. By default, data is replicated to two other places in the cluster. A pipeline is built between the three data nodes that make up the pipeline. The second data node is randomly chosen on a rack other than that of the first replica of the block. This is to increase redundancy. The final replica is placed on a random node within the same rack as the second replica. The data is piped from the second data node to the third. To ensure the write was successful before continuing, acknowledgement packets are sent from the third data node to the second, from the second data node to the first, and from the first data node to the client. This process occurs for each of the blocks that make up the file. Notice that for every block, by default, there is a replica on at least two racks. When the client is done writing to the data node pipeline and has received acknowledgments, it tells the name node that the write has completed. The name node then checks that the blocks are at least minimally replicated before responding. This lesson continues in the next video.